The second class of discrete time or digital filters that we are going to cover in this course are infinite impulse response filters, in short, IIR filters. We'll start again with the motivation or the general idea behind this class of filters. Infinite impulse response filters can be understood as a discrete approximation of ordinary differential equations. Consider, for example, this first-order ordinary differential equation. The output y of t could maybe have this form here, and we want to approximate its first derivative at a given time capital T, which we assume is equal to k times the sampling period Ts, such that the first derivative can be approximated as the slope of the line between y at time capital T, which is equal to y at time k times Ts, and y at the next sampling instance, which is y at k plus 1 times Ts. Since the time between the samples is equal to Ts, the slope of the triangle is equal to y at k plus 1 times Ts minus y at kTs divided by Ts. This is now used as an approximation for the first derivative of y at time k times Ts, so that the ordinary differential equation at time t equals k times Ts is approximated by this slope plus a times y at kTs equal to b times x also at time k times Ts. Using discrete time signal notations, y at k plus 1 is hence equal to 1 plus a times Ts, y of k, plus b times Ts, x of k. For convenience, we denote the factors 1 plus a Ts as alpha and b times Ts as beta, such that we get the input-output equation of this first-order infinite impulse response filter y at k plus 1 is equal to alpha y of k plus beta x of k. To see why this filter is an infinite impulse response filter, let's evaluate the output y for some time instances k. We'll start with y of 1 equal to alpha y of 0 plus beta x of 0. Then y of 2 is equal to alpha y of 1 plus beta x of 1. But since we already have an expression for y of 1, this can be written as alpha squared times y of 0 plus alpha times beta x of 0 plus beta x of 1. Following the same steps, we can find the expression y of 3 is equal to alpha to the power of 3 y of 0 plus alpha squared beta x of 0 plus alpha times beta x of 1 times beta x of 2. We can also find the general expression that y of k is equal to alpha to the power of k y of 0 plus the sum from n equals 1 to k of alpha to the power of n minus 1 times beta times x at time k minus n. So the output at time k depends on the input signal x of k for all times between 0 and k minus 1. So as time k tends to infinity, the output y will depend on all previous input signals x, which can be interpreted as the impulse response of the system h of k having an infinite range. Hence the name infinite impulse response filter. But of course, when implementing such a filter, we will not use an expression including an infinite impulse response. Instead, the input-output equation with a finite amount of terms is implemented. The input-output equation of a general, causal infinite impulse response filter is given by y of k plus alpha 1 y of k minus 1, and so on up until plus alpha n y of k minus n, equal to beta 0 x of k plus beta 1 x of k minus 1, and so on up until beta m times x of k minus m. In contrast to the input-output equation of finite impulse response filters, the output y at time k doesn't only depend on the input signal x, but also on the output signal at previous sampling instances. Applying the Z transform to the input-output equation allows us to derive the transfer function of the system h of z, which is defined to be equal to y of z divided by x of z, so that the transfer function is given by a numerator polynomial with coefficients beta divided by a denominator polynomial with coefficients alpha. By substituting the complex variable z in the transfer function, we can also find the frequency response of the filter in normalized frequency and in real frequency.